Okay. Hello and welcome to today's lecture for CS 303 Operating Systems. Today we have chapter number 5. So we are talking about CPU scheduling, and within chapter 5 we have lecture number 5. Okay. So as you can see, this is quite a rich area in terms of the kind of research that has been done. Many algorithms have been proposed. We are only looking at some of the most important ones. So a lot of work has been done, in this scheduling area. So we today we look at two major topics: multi-level queue scheduling and predicting CPU bursts. So multi-level queue scheduling, as the name suggests, here instead of one ready queue, we have multiple ready queues. So up till now we have been assuming that we have only one ready queue. So any task that needs the CPU for executing instructions, or any task which is in a ready state, obviously it will be inserted to the ready queue. And then the CPU scheduler, based on the algorithm that it is employing, it is using, it will pick up the next task from the ready queue. So now we will look at a special case of this, in which we have not one but many ready queues. So why do we need it? How does it work? We will be discussing that. Second part is predicting CPU bursts. So up till now, whatever algorithms we have discussed, for each process, one main or one major quantity that we need so that the scheduling algorithm can work is its execution cost, right? So which means how long is the process going to take. So this obviously depends on the instructions. Right, depending on how many instructions it has. It also depends on the type of instructions, right? So if it is doing division, right, versus if it's a simple load and store, they may have different execution costs. So for each process, the number of instructions that have to execute and the type of instruction that have to execute have an impact on the execution cost. Right. So when we are saying execution cost or CPU burst time, what we are saying is the time required to execute the instructions of this process. Okay. So that is what we mean. So for each algorithm, we are given that quantity, and that is indeed very useful, because if you are doing something like shortest job first, well, we need to know the burst times. Only then we can arrange them such that the shortest burst time comes first to execute, and then longest burst time comes last. So we need to know the burst times, right? Even for real time scheduling, when the task will end, it depends on how much its execution cost is, right? And then we can see whether it has met its deadline or not. So knowing the CPU burst is important. Now the issue here is one assumption we are making to simplify things is that the CPU burst times or the execution costs are known in advance. So this may or may not be true. If we know which process is going to be executed and what action it is going to do, which instructions it is going to execute, then we can make an assumption that this is the CPU burst time. If we don't know which process is going to execute, then we don't know the CPU burst time. So is the next process going to be a web browser, right? Or is the next process going to be a bash shell? Or is the next process going to be a game? So with a dynamic system, we don't know. So then if we don't know the CPU bursts, then we are in a bit of a trouble in terms of the running of the scheduling algorithm, because knowing the burst time is critical for the scheduling algorithm. Well, not for all of them. First come first serve may still work. So no matter what the burst time is, that algorithm can still work. When whatever job comes, whenever it comes, it just enters a ready queue and then first come first serve they are serviced. But for other algorithms, especially for priority based ones, we do need the burst times. So if we don't know what the burst time is, if we don't know which process is going to come because it's a dynamic system, then what do? Right? So with regards to that, there are techniques using which we can predict. So if we don't know for sure, then we can predict. And then based on some technique, some statistical analysis perhaps, we can predict the CPU bursts. And then in our scheduling algorithm, we use those predicted CPU bursts. So we say, okay, predicted CPU bursts are 8, 9, 10. So for shortest job first, the one with 8, then with 9, then with 10. So these are the topics for today's lecture. Okay, now I am on slide 2 and we're just comparing CPU versus IO bound processes. So this will be used later in one of our algorithms. So we're just sort of revising this. So we know the difference between CPU bound and IO bound processes. CPU bound spends most of its time doing CPU activity, right? So an example that of a CPU bound could be any batch job, or let's say doing some DNA calculations, perhaps multiplying two very large matrices. So the hallmark, the feature of all these jobs, all these processes is there is little or no IO activity, and most or all of the activity is running instructions on the CPU. So they are CPU bound. IO bound spend most of their time doing IO activity, right? So CPU activity is little or no. So any kind of interactive job, right? Let's say database in which you search for flights, right, from Delhi to Chandigarh, and then click search, and then it looks at the database, gives you all the options, and then again you search like a travel agent. So here the actual CPU time is spent in doing what activity? Taking the search strings, the source city, destination city, and searching at the database, and outputting all entries with the specified source city and the specified destination city. So that kind of database search happens very quickly. But then how much time is elapsed before you do the next search? Well, it could be 5 seconds, it could be 1 minute, it could be 1 hour. So like that. So that is an example of IO activity or IO bound, right? So question we have is, should the scheduler distinguish between CPU and IO bound processes, and how should it schedule them? Okay. So if I have both CPU and IO bound, how should I schedule them? So if you recall, we looked at this question in the beginning, and what we discussed was that it's probably better to give to schedule the IO bound processes first, because what happens is if you schedule the CPU bound early, then one CPU bound will block the execution of many IO bound. So the IO bound will take the IO bound processes will have to wait in the ready queue for a long time before they get the CPU. As a result of this, the average wait time, which is a good metric to measure the success of a scheduling algorithm, average wait time will increase. So consider the scenario in which you have one CPU bound and 10 IO bound. So if you if you schedule the CPU bound first, then those 10 processes have to wait for a long time. So the logic is, anyway, the IO bound processes need the CPU for a very short duration. So why not give a higher priority to the IO bounds? So IO bound 1 comes, uses the CPU for a very short time, goes off to do IO. Then 2, 3, 4 all up till 10. So in a very short amount of time, all 10 have used the CPU, they're all off to do IO. So which means in a very short amount of time, 10 of your 11 processes have been serviced. So good throughput, good average wait time. And then you give it to the CPU, and then CPU will execute for long. And now because the IO takes long, by the time CPU finishes, you have a good chance that among those 10 processes which went to do IO, at least some of them will be ready for CPU once the CPU bound process is executed. So by the time the CPU bound process finishes, good chance that many IO bound processes are again ready to execute. So this kind of scheme I think would work well. Okay, so better usage of computers resources if IO bound gets priority over CPU bound, because if you give it to the CPU bound first, your IO devices will be underutilized for a long time, because IO devices can only be utilized once the IO bound processes have gotten the CPU. So your IO devices will be unutilized for a long time. But if you give the CPU to the IO bound first, very quickly they'll execute and they will go straight to the IO devices. So utilization will be quite good. So in general, when you have both, it's good to give IO bound more weightage, okay, more priority, right? Okay, so now I am on slide 3, and now we talk about multi-level queue. So far we assume that we have one ready queue and we pick processes to execute from that queue. So as we discussed, process arrives into the system, it ready to execute CPU instructions, goes straight to the ready queue. From it the CPU scheduler picks, and how does it pick? Depends on the scheduling algorithm, right? So that is how, the assumption that we have worked with, only one ready queue from which we pick. Right. Now what we are saying is sometimes it makes sense to group processes together. So sometimes it makes sense to have we have different categories of processes. So for example, if we have one system in which we are processing both regular processes and real-time processes. So how do we distinguish between the two? For real time we have to meet the deadline, most important. For regular processes there is no deadline, so but still we have to execute them quickly. So note that executing quickly or as quickly as possible is not necessarily the same as meeting deadlines, because in real time you can actually delay the execution of a process if you can still guarantee that deadline will be met. Okay. So what we are saying here is because of their characteristics, it makes sense to group processes together. So you have a bucket of regular processes, right, and a bucket of real-time processes, and now you have to schedule both of them. So you have one OS in which you have both these processes. Now you have to schedule. So key concept here is you have multiple queues, one for each type of process, and the nice thing here is you can adopt different scheduling algorithms for different queues. So for the regular processes, maybe you can do for fairness, you could do round robin. So each regular process gets a CPU for a specific time, the time quantum, and then CPU is given to second one and third and fourth. So round robin for the regular ones. For real time ones, you decide to use earliest deadline first. Okay. So look at it in terms of the design. You have two ready queues, one of regular processes for which you are using round robin, and one for real time processes for which you are using earliest deadline first. So two scheduling algorithms are being used. Now other kind of interesting scenarios can arise. Now that you have two ready queues, which one do you go to first? So perhaps looking at this particular case, the real-time processes could have absolute priority over regular ones. So which means till the real-time queue is empty, you don't execute any regular processes. Of course not, it's not that simple, because if you have a continuous stream of real-time processes coming in, what would happen to the regular processes? They would be starved. So perhaps you can have aging. So, but definitely the real time queue needs to have some kind of precedence over the regular queue. So, this is multi-level. We have multiple queues. Generally, in each queue, we have a specific kind of type of jobs, and the flexibility is that for each queue we can employ a different algorithm. So, note that this is better than having one queue, putting all the regular and real-time processes together in that queue, and using single scheduling algorithm. Because if you use round robin, real time may not work. If you use real time, it may not be beneficial for regular processes. So the best way is to separate them, create separate queues, separate ready queues, and then apply a specific algorithm to each queue. Okay, so this is a multi-level queue. Okay. Okay, so now I am on slide 4, multi-level queue. And here what we are saying is that we have different priority levels, and then for each priority level we have a separate queue and a bunch of processes in it. So up till now we have assumed only one queue, and there are no priority levels, but there is a priority value, right? 0, 1, 2. Here what we are saying is a bit more involved. We have priority levels. So the ones with top priority, they are priority level 0. Then next highest 1, then 2, and then all the way till n. And now what you do is schedule the process in the highest priority queue. So your policy could be, first go to the queue with priority level 0. Keep on executing based on your algorithm. Once priority 0 queue is finished, go to priority 1, then priority 2, and then up till n. So what we are saying is for each priority level we have a separate queue with a number of tasks in it. Okay, so given a set of processes, you identify that these 5 processes are the most important, put them at 0. Then you identify these 3 processes are next most, then 1. Then these 4 come below level 2. So of course you need some kind of metric to identify the higher, to identify the priority level. So perhaps the top one could be hard real time, in which the deadlines must be met. Second level could be soft real time, in which you can miss some deadlines. And then you can have non real time, perhaps a level 2 IO ones, then level 3 CPU ones. So like that, depending on your requirement, you can have different levels. So here what we are saying is, you can have levels of priority. So all processes in a particular queue, they have the same priority. So here T0, T1, T2, T3, T4 all have the same priority, and then T5, T6, T7 they also have the same priority. So this is a bit more fine grained. It allows you to define priority levels, and then so whenever you have complex requirements in which you've got real time tasks, and within real time you've got, let's say, hard real time, you've got soft real time, and then non real time you've got CPU bound, you've got IO bound, different. So whenever you have a very complex mix of tasks, so having these different priority levels, that can really help. So idea here is top level is the first to execute, followed by level 1, then level 2, all the way till level n. Okay. So here I am on slide 5, multi-level queue, and as we were discussing in the previous slide, this prioritization can be based on process type. So here we see highest priority could be for real-time processes, right? You have to meet the deadlines. Second highest priority could be for the system processes, or we call kernel processes. So if you're given a job, because the kernel processes manage all the user applications or the kernel threads, so perhaps given a choice between user and kernel processes, uh, higher importance is given to kernel processes. So second level, system or kernel processes. And then among user processes, probably first interactive, then batch. Interactive are IO bound, batch is CPU bound. So in this way, all the real-time processes you have, put them in one queue. All the kernel system processes in another queue. All the interactive processes third queue. All the batch processes fourth queue. And now you can try to schedule. Okay, so you can have different algorithms for each, right? For real time, you could use earliest deadline first. Again, for kernel processes, you would need to see maybe first come first serve if you want to use that. Then for interactive and batch, you could have a priority based scheduler which says that only when the interactive process queue is empty will I execute the batch queue. So because we are giving more priority to the IO bound, we just discussed that. So we execute batch processes only when the interactive process is queue, right? And the system process is queue and the real-time process is queue, all are empty. So you can go many ways. It gives you a lot of flexibility. You can have separate algorithms for each queue or same algorithm for all the queues in some manner. A lot of flexibility. Okay. So now I am on slide 6. Now looking at the previous slide where we have 4 queues: real-time, system, interactive and batch. So now the question is how do you schedule among the different queues? Right? Which one goes first, which one goes second and so on. So you have some options. Option 1 is assign a fixed priority to each queue. So you say real-time queue is the highest, then system, then interactive, then batch. So which means first you'll here again I'm assuming I have a single CPU. Of course, if you have multiple CPUs, your job is made a lot easier. But if you only have one CPU, then you say highest priority is real time, then followed by system, followed by interactive, lastly by batch. So then what you're doing is you execute a system process only when the real time queue is empty. You execute an interactive process only when the real time and system queue is empty. And you execute a batch process only when the real time, the system and the interactive queue is empty. So that's one way to go. Right? What we have done here is assign a fixed priority to each queue and then we move. So only when highest priority queue is empty, we execute the other one. So this can be a good approach, but there could be issues here. And what is a major issue in this case? Now because we have priorities, so one problem that's always there with any priority based scheduling algorithm is starvation. So if you have a continuous stream of real time and system and interactive processes coming in, your batch processes could starve. They would not make. So generally for batch processes people are more tolerant. If it takes 1 hour more they may be okay, but still there is a potential for starvation for the lower priority queues. So how can we tackle that? Well, we could do aging. So the longer a batch process spends, the higher is its priority. Eventually it gets a CPU. Or we could do something which is would be more elegant. We could assign a time slice to each queue. So sort of like a round robin. Time slice to each queue, keeping the priorities in mind. So which means each queue does not get the same time slice. Why? Because now we have priorities, and therefore what we would like is the queue with a higher priority gets a longer time slice. So we could say fine, in this case the real time process will get time time slice for this would be, well, 500 milliseconds. For system processes, it would be, well, 100 milliseconds. Interactive even less, batch even less. You could do that, right? Or you could have a policy. So we are assigning a time slice to each queue. Each queue gets its own time slice which it can use to schedule its processes, right? So you say that 80% of CPU time to EDF, 20 to round robin. So let's say what we have in this case is, for the real time processes we are doing EDF, and for the rest of them we are doing round robin. So note that we have a lot of flexibility. Either we have we can have a different algorithm for each queue, or multiple queues can share the same algorithm. So what we do here is, for real time we have earliest deadline first, and for the rest of them, the non-real time ones, whether it's system or interactive or batch, for all three we are using round robin. Okay. So then what we say is perhaps 80% of time to real time queue, 20% to round robin, right? And the reason for that is because the real time ones are have a higher priority, so we give them longer, or we give them a larger chunk of the CPU time. So note that this is different from giving the vanilla version of round robin. So vanilla version gives the same time slice to all processes. 4 processes, each gets 5 milliseconds. So looking at the same example, what we can say is, let's say among those 4 processes, one of them is real time. P1 is real time, P2, P3, P4 are non-real time. So instead of giving 5 milliseconds to all, to P1 we give 10 milliseconds. And to P2 to P4 we give 5 milliseconds. Or if all 4 have different characteristics, P1 we give 20 milliseconds, P2 15, P3 10, P4 5. So you get the main idea. The main idea here is the process which is more important, the process with a higher priority, gets a longer time slice. So or you can say the 1 unit of a time slice is 5 millisecond, and the real time will get 4 units at once. So a process with a higher priority will get multiple time slices together, right? Why? Because just to ensure that it gets more time on the CPU, so it can be finished sooner, right? So if it's a real time one, you give it more time, there's more chance it will be finished sooner. If you keep the same quantum for all, then the real time they may miss it, right? So for example, if the deadline is 10 and you're giving 4 processes, you're giving 5 milliseconds, P1 is real time, deadline is 10, 0 to 5 it runs, then 5 to 10 some other one runs, P2 runs, 10 to 15 P3, 15 20 P2, then 20 to 25 remaining of P1 runs, it misses a deadline. But if we give it 10 in one shot, it meets. So that is a general idea. So we're doing it, note that we are balancing things. We are giving more CPU to the higher priority processes, but at the same time, because we're doing round robin, we're ensuring that the lower priority processes do not starve. So even the lowest process here, P4, will still get 5 milliseconds, and then the cycle repeats, right? 20 millisecond to P1, 10 to P2, or 15 to P2, 10 to P3, 5 to P4. So we're trying to do a balancing act. We're giving higher time quantum or more time to the higher priority processes, and at the same time the lower priority processes are not starving because we're doing a round robin thing. So see that it is a sort of balancing both. Because if you do plain priority based, leads to starvation of lower priority. So we don't want that, so we're doing round robin. But within round robin, higher priority ones, they're getting the CPU for longer. Okay, so I hope it's clear, right? Okay, now I am on slide 7. Okay, slide number 7, multi-level feedback queue. So this is a special case of a multi-level queue, multi-level feedback queue. So what is so different here? So in the previous case of multi-level queue scheduling, the assumption was that the processes are fixed to a queue. So generally what we are saying is that makes sense also. A real-time process will remain a real-time process. So it doesn't make sense for it to go to a system process queue or interactive process queue or batch process queue. So in the previous case, the assumption was processes are fixed to a queue, which means they cannot move along or they cannot travel from one queue to the other. So now if we relax this assumption and if we allow for queue movement, which means a process enters in a particular queue, but during the course of its execution, it can move to another queue, and then a third queue, and then a fourth queue. Okay, so this becomes a multi-level feedback queue. So you have many levels of queues, multiple queues, with the additional feature that a process can travel from one queue to the other. So multi-level feedback queue. Okay. So the advantage of this could be that for each process the scheduling algorithm or can change. So sometimes you may need that. Okay. So sometimes you may say that okay fine, this process entered the ready queue, this process got the CPU, and now that it has gotten the CPU, let the priority of this process reduce a bit so that others also get a chance to run. And then when it gets some more CPU, again reduce a bit. So for fairness, you may want that. So to motivate this, let's look at an example. So here we have, this one doesn't show the picture, but a picture will come. So we have a system in which we've got 3 queues. So if you have your textbook with you, you can let me just open it up, and this should be on so multi-level feedback queue scheduling is on page 215, 215, and then on 216 we have figure 5.7 multi-level feedback queue. So page 216, 216, figure 5.7 multi-level feedback queues. So here we see 3 queues. Top one, it says quantum is equal to 8. Middle one, it says quantum is equal to 16. Bottom one, it says FCFS. So what do we do we discover looking at this? So we have definitely 3 queues. It's a feedback queue, so a process can move along from one queue to the other. And you have some arrows here, right, which shows one scenario could be a process enters a queue, finishes execution, and leaves the queue. Another scenario could be a process enters a queue, does some execution, so still some execution is pending, still some instructions are pending, so it goes on to the next queue, right? So that's what the arrows show, and what it looks like is Q1 and Q2 are using round robin with different quantum values, and Q3 is using FCFS. So we have 3 queues, Q0 using round robin with time quantum 8 milliseconds, Q1 round robin with time quantum 16 milliseconds, Q2 FCFS first come first serve. So among these queues we say which one has the highest priority, generally the top one, Q0. Which one has the lowest priority, Q2. Middle one, Q1. Okay. So this is the system we have. Okay. Okay, so now I am on slide 8, and here we see the picture that we were talking about, multi-level feedback queue. queues. Sorry. So 3 queues you can see. So quantum 8, round robin with quantum 8 for Q0, round robin with quantum 16 for Q1, and first come first serve for Q2. So we can see a process arrives in Q0. Either it finishes, that's one scenario. Other scenario is still has some computation left, so it goes to Q1. Then either it finishes or has some computation left, then it goes to Q2. So a thing to be noted is whatever part of a process is finished in Q2, all those instructions are executed. So let's say if a process goes to Q0, runs 15%, then it goes to Q1, runs 35%. So how much has it run? 50%. 50% is left. Then that 50% it will do in FCFS itself. So once it's in FCFS, it will only get out once it finishes. So whatever is finished, when its turn comes, all the remainder of the instructions will be executed in FCFS. So if a process is exiting FCFS queue, it can do that only in one scenario, when it has finished execution. Okay. So this is our scheduling scheme. Round robin and first come first serve. Round robin first, and even within round robin, two different quantums. So you can see this is a flexibility. Not only are we executing different algorithms on the same system, but in one particular case, even for the same algorithm, we are employing different flavors of it. So even within round robin, we have two versions going, one with quantum 8, one with quantum 16. So lot of flexibility. Okay. So now I am on slide 9, and now we are going to look at how a process would move among these queues. So as such, what is a scheduling algorithm? So obviously what happens is a new process enters the queue. Which one? Q0. So new process enters Q0. So eventually its turn will come. It's a ready queue. When it gets the CPU, it receives exactly 8 milliseconds. So two scenarios. Either those 8 milliseconds are enough to finish. So perhaps it needs only 4 milliseconds. Then after after just 4 milliseconds elapse, it's done. So if its execution cost is less than or equal to 8 milliseconds, it's done. Otherwise, if it's more than 8, that means if it does not finish in 8 milliseconds, it's moved to tail of Q1. So note that in Q0, process may have to spend time. It's a ready queue, so first come first serve within that. If Q0 has 5 processes, then depending on which order they arrive, they will be given the CPU, but only for 8 milliseconds at a time. So if the process does not finish in 8 milliseconds, process is moved to the back of Q1. So there again it has to wait its turn, and when its turn comes, it receives 16 additional milliseconds. So here again, if its remaining execution time was less than or equal to 16 after it executed on Q0, which means if the total cost was less than or equal to 24, then at Q1 it will finish execution. If it still does not complete, that means if its execution cost was more than 24 milliseconds, again it is preempted and moved to the tail of Q2. So once it receives 16 milliseconds in Q1, we are doing preemption, right? So we are interrupting its execution and transporting it to the last queue, and then for Q1, the next one in the chain is going to be executed. So then it goes to Q2, and in Q2 it is scheduled in first come first serve fashion. So whatever is percentage of it is left, so let's say it was 30 milliseconds. In Q0 it gets CPU for 8 milliseconds. In Q1 1 for 16. So then how much will it execute in Q2? 8 plus 16, 24, 30 minus 24, 6 milliseconds. So whatever is the remainder, whatever is the balance, milliseconds, they will finish in Q2. So how are jobs put in queues? Using FCFS. So within each queue also it's FCFS, right? So for Q0, whichever, so at once let's say if 10 processes are ready, they all enter Q0 in a first come first serve basis. Likewise Q1 also first come first serve. Q2 of course first come first serve. So here we are talking about how are processes inserted into the queue in the order in which they become ready. Okay. So now the question is, what kind of processes is this algorithm partial to? So we know how the algorithm works. So now we ask ourselves, what kind of processes is this algorithm partial to? Which processes does it prefer? So let's talk in terms of CPU and IO bound. So will this algorithm prefer CPU bound processes or IO bound processes? So generally it will prefer IO bound, right? So because what is the defining characteristic of an IO bound? It uses very little CPU. So consider a process IO bound process which needs less than equal to 8 milliseconds. So that process will finish execution the earliest. Why? Because less than equal to 8 CPU. So it enters Q0 and it gets out. It is serviced pretty quickly. Whereas which kind of processes have to wait the longest? Obviously longer processes which are, let's say, more than 24 milliseconds. So any process more than 24 milliseconds has to go to Q2. So here again what we are saying is the time between when a process is ready and when a process is finished. So long processes will take longer to finish because they will have to hop, they will have to jump among queues, and anytime you enter a queue you are not entering at the head, you are entering at the tail, so you have to, there can be considerable wait time in each particular queue, whether it's Q0 or Q1 or Q2. So any process less than equal to 8 milliseconds will finish execution the fastest. The longer a process is, the more time it will spend. So definitely partial to IO processes, right? I hope that's clear. Because the short processes, they will most likely finish in Q0 or Q1, right? Longer processes, they will go up till Q2, right? So now I am on slide 10. So here we just putting in words what we discussed. If Q0 is empty, then process in Q1 starts execution. So that's another thing. How do we distinguish between the queues? So we can say perhaps Q0 has absolute priority over Q1. Q1 has absolute priority over Q2. So which means we can execute from Q1 only when Q0 is empty, and we can execute from Q2 only when Q1 is, and Q0 of course, both are empty. So if Q0 is empty, processes in Q1 can start execution starting from the head. Processes in Q2 are executed only when Q0 and Q1 are empty. So we have that absolute priority. Okay, so scheduling algorithm gives highest priority to any process with execution time of 8 milliseconds, 8 units or less. Because such processes, they enter Q0 and they get out of Q0. Note that whenever a process has to jump from one queue to the other, that's additional overhead. Additional code has to be run, and then when it enters the new queue, it always enters at the back. So that wait time is also added, right? So such a process will enter Q0, eventually run and finish. Next highest priority is for processes whose execution time is between 9 and 24. So they will finish in Q1. And processes with execution times more than 24 will end up in Q2 and run only if Q0 and Q1 are empty. So note that a process compare two processes, one with execution cost 25, another with execution cost 100. And if the one with the 100 comes before the one with 24, then the one with 24 may have to wait for long. So beyond 24 milliseconds, it's just a first come first serve. Okay. So definitely, because we have a absolute priority, we can have starvation. So if you have a continuous stream of processes coming in Q0, then processes in Q1 and Q2 can starve. If you have a continuous stream of processes coming in Q1 and Q2, Q0 and Q1, then processes in Q2 can starve. Right? So we definitely can have starvation here. Right? So question is, how can we prevent this? Okay. So once again, how can we have can we have starvation here? So starvation means for a particular type of process, they're taking a long time to execute. Right? That is the question we have to think about, which I will give that to you as an exercise. So question here is, in this multi-level feedback queue scheduling scheme that we see here, can there be starvation? Which means, can we have a scenario for which or in which a particular type of process will have to wait for an extremely long amount of time? So can we have starvation, or can we say that there is no starvation? No matter what kind of process it is, eventually it will finish in a reasonable amount of time. So think about it. Can we have starvation here? If so, what can we do about it? If not, then it's okay. So I will give you this as an exercise. Think about it, and then we can discuss in one of the live sessions. So think about whether we can have starvation or not in this particular algorithm. Okay. So algorithm is clear. Process arrives, enters into Q0, gets CPU for 8 milliseconds, let's say. Then it either finishes or it enters Q1, gets CPU for 16 milliseconds. Either finishes or enters Q2, where it's scheduled first come, first serve. And it finishes. So can we have starvation or not? Think about it. Okay. Okay, now I am on slide number 11. And topic of these slides is, the next couple of slides is predicting CPU bursts, which means knowing the future, right? So what we're saying is, in priority based scheduling, for example, one example is shortest job first. So this is based on, the scheme is based on assigning priorities based on CPU burst times, right? So you need to know the CPU burst time, and only then can you sort them and execute the algorithm, shortest one going first. So processes with smaller next CPU burst times are assigned a higher priority. So typically what happens is, you have a CPU burst and IO, then CPU burst and IO. So what we are scheduling on is size of the next CPU burst. So just to simplify the things, we're just taking one execution time, so start to finish. Although in reality what happens is, you have a CPU burst and IO burst and CPU burst and IO burst. So what we're scheduling based on actually is size of the next CPU burst, right? In first come first serve round robin, processes are serviced in their arrival order, right? So it doesn't really matter, how long the process is. Depending in first come first serve, whenever the process comes, depending on that, it gets some scheduling order. It goes into the queue, and then when its turn comes, it executes, no matter what its length is. Round robin, again, length does not matter much, because our goal is to just give it some to periodically give the process the CPU for how long? For the length of the time quantum. So if it's a long one, it takes more quantum, short one takes less quantum, doesn't really matter. But for priority based schemes, knowing the CPU burst is extremely important. Okay. So only based on that you will do the calculations. So for priority based schemes, the challenge is knowing the length of the process CPU bursts. Right. So we don't know the future CPU burst of processes. So first of all, we don't even know what process is going to arrive in the system. And even if we know the process, we don't know the length of the CPU burst. Right. If I know that Microsoft Word is coming, I don't really know, which operation the user is suggesting within Microsoft Word. The whole thing is real time. So are they going to do? Are they going to select all the text and do a word count, or are they going to print the document, or are they going to make some formatting corrections? We don't know, because depending on the action that they do, that leads to specific instructions, which leads to a specific CPU burst time. So knowing the future CPU burst times, it is a tricky problem. Okay. So one option is we use worst case execution times. So we say in the worst case, a process will its execution cost is 10 units. So within the CPU, while we are provisioning, while we are scheduling, we reserve 10 units for that process. Now the process may only in reality take 8 or 9 or 6 or 7. So in that case, we are wasting resources. If you reserve 10 units and if a process takes 7, then those 3 are wasted. Could have been given to some other process. So one option is we can use worst case execution times, right? So but the problem is process execution time can be lower. The process can execute quicker. So it would be a better approach if we could predict the CPU burst times. So the goal is to predict the CPU burst, the current CPU burst, or the next CPU burst with the help of past CPU bursts. So for each process, you try to analyze its patterns. So because it will have sort of a sequence of CPU and IO bursts. So for the past CPU bursts, try to analyze what their length is or what their lengths are, and based on that, try to predict what the future lengths are going to be. Okay. So maybe we can expect that the next CPU burst will be similar to the previous CPU bursts. So if you're looking at a database search, so every search is a search on the same database. So it might take similar amount of time, same or similar, right? So and then use this predicted CPU burst in making scheduling decisions. So once again, what's going on is the CPU is executing, it's requesting, the process is executing in real time, it's requesting CPUs as a CPU in specific bursts, and we keep a track of the past CPU bursts, and then based on that we try to predict, based on the past behavior, we try to predict the future behavior. So based on the past CPU bursts, based on that pattern, we try to predict the CPU burst of the future. And then we use that predicted CPU burst in making scheduling decisions. So for shortest of first, that would mean for a set of processes, we have predicted the next CPU bursts, and then whichever one is smallest, we schedule it first. Okay. So I hope the problem is clear, and I hope the general approach is clear, right? Okay, now I am on slide 12. And now we're discussing one particular technique for predicting the CPU bursts. So this is the formula we have. Tn plus 1 is equal to alpha times Tn plus 1 minus alpha Tn, small t and large t. So what are these quantities? Small t subscript n is the actual length of the nth CPU burst. Okay. So the actual or the real length of the nth CPU burst of a process. Large Tn plus 1 is the predicted value for the next, which means the n plus 1th CPU burst. Okay, so once again, small t subscript n is the actual length of the nth CPU burst, and large Tn plus 1 is the predicted value for the next CPU burst. Okay, and what is large Tn? So large T is a prediction, so large Tn is a previous prediction used to schedule the most recent CPU burst. This is a weighted value from past iterations. So you can take sort of a weighted average. So one option could be, you have those previous CPU bursts and you take the average of all of them, saying the next one will be equal to this. Or you will take in a simplistic way, they are same. Right? So Tn is a previous prediction used to schedule the most recent nth CPU burst. Yeah, so that is a weighted average, and alpha is a value between 0 and 1. The reason alpha is there is so that we can tweak the weightage given to Tn and the weightage given to we can tweak the weightage given to small t n and the weightage given to large Tn. So what do we mean? Well, when alpha is 0, what happens to the equation? Large Tn plus 1 is equal to Tn. So which means the most recent real actual CPU burst can be ignored, and the predicted value of the next CPU burst is the same as a weighted value from the past iterations. Okay. If alpha is 1, then the equation becomes Tn plus 1 is equal to Tn, which means the prediction for the n plus 1th CPU burst is the same, is equal to the value of the last burst. So the next burst will be exactly same as the last burst. Okay. So which means only the most recent CPU burst matters. Ones before them, they can be ignored. So once again, alpha is 0 means most recent CPU burst is not important. Weightage average is important, and alpha is 1 means the weighted average is not important. Only the most recent CPU burst is important. Weighted average of the previous bursts. So what we'll do in our example is take alpha equal to 1 by 2, which means half weightage is given to the previous CPU burst and half weightage to the value from the past iterations. Okay, so in this way we will calculate. Okay, so now I am on slide 13. Prediction of length of the next CPU burst. Right. So now let's see. So we're given a graph. There are two values. One is CPU burst, the actual value, and one is the prediction or the guess. T is the actual value, tau is the prediction. And looking at the graph, you can see this sort of following each other. Not much difference between them. So first we need a seed value, a guess value, which let's say is 10. Right? It could be anything. Maybe the average so far. But let's pick 10. So weighted for previous one is 10, and then most recent CPU burst is 6. So now what's the prediction for the next burst? Now the weighted value is 10, previous actual value is 6, so half weightage for both. So 10 by 2, which is 5, plus 6 by 2, which is 3, 5 plus 3 is 8. So our prediction for the next one is 8. Now moving along, previous prediction is 8, so weighted is 8, and a real is 4. So 8 by 2 divided by 4 by 2. 4 and 2, 6. Right. Now 6 and 6, prediction is 6. 6 and 4, 6 by 2 is 3, 4 by 2 is 2, 3 into 5. 5 and 13, 2.5 plus 6.5, 9. 9 and 13, 6.5 plus 4.5, 11. 11 and 13, 5.5 and 6.5, 12. So in this way we can calculate the values. What we are given here is the actual CPU burst, right? Actual CPU burst and the past value, past history value, which we are modifying, right? It's becoming 10, then 8, then 6, then 6, then 5, then 9 and 11. Finally 12. So at each particular point when we have to do a calculation, we are given two values, past weighted value, which is 10 to begin with, and the actual value of the previous CPU burst. Both get equal weightage. So latest actual value for the latest burst divided by 2 plus the information on the past or the values of the past bursts, that weighted information divided by 2, and then that's a predicted length of the next CPU burst. So 10 is the history, maybe weighted average. 6 is the most recent one. So 10 by 2 plus 6 by 2, 5 and 3, 8. So now the weighted one has changed from 10 to 8. Why did it change? Because some weightage we took from 10, some weightage we took from 6. And then 8 and 4, right? Again equal weightage, 4 plus 2, 6. So from 8 it's again becomes 6 because half from 8. So you want to give half weightage to the previous values and half weightage to the latest one. So in this way, we can calculate and we get the predicted value. So I hope this is clear. Once again, we need the actual value of the last CPU burst and the previous weighted. Give half to both, get the predicted one for the new one. Okay. And then that predicted one and the next weightage again average, get the next. So in this way we approach and we are able to predict the length of the next CPU burst. Okay. So I hope it's clear, right?